Good morning, everyone. I'm Marcio Carvalho, and I want to first thank Lisa for organizing this virtual meeting. All the talks from yesterday and today, there have been quite interesting. And I'm going to talk about the work that we've been doing at PUC in Rio on microscale physics of oil displacement in porous media. So usually during oil production, water is injected through injecting wells, and this water will push oil towards the producing wells. The amount of oil that you produce is a function of how well the reservoir is swept by the water phase. So this is a macroscopic phenomenon. And because the water is less viscous than oil, typically a large portion of the reservoir is not swept by the water phase. And also it's a function of how well the oil displaced in the areas that the water swept the reservoir. So even in areas that were swept by the water, a certain amount of oil gets trapped by capillarity. So this is a microscopic physical phenomenon. So every enhanced oil recovery method will try to attack one of these phenomena, or preferentially these both factors. So in this talk today, we're going to focus on the microscale flow physics. So even in the areas where the reservoir was swept by water, as I mentioned, there are oil ganglia that get trapped by capillarity. So if you want to displace these oil ganglia and reduce this residual oil saturation, the pressure difference in the water phase has to be stronger than the capillary pressure that keeps this ganglia immobile. So there are two ways of achieving this mobilization. One is reducing the capillary pressure, for example, by reducing the interfacial tension between the water and the oil phase. And another way is to increase the pressure difference in the water phase. And what I'm going to discuss in this presentation today is two work that we've done lately, that we use complex fluids to try to control this pressure difference in the water phase and therefore mobilize trapped oil ganglia. So we use flow visualization in order to study this porous scale phenomena. And we use two different types of visualization. The first one is visualizing the flow in a two-dimensional model of a porous media. The one that I'm going to be discussing here, we presented in a recent paper last year. And it's made out of a regular network of constricted capillaries, but the capillaries have constriction of different sizes, and they're randomly distributed over the pore space. This model is made out of glass, so which gives us very good imaging. So it's we get improved visualization. It's easy to control the surface properties, so we can have water or oil wet porous media, and it can achieve can sustain high pressure. So we can get a pretty high pressure in some of these experiments. So here's an example of the type of visualization. Water is with the red dye in this case is displacing oil that's a higher viscosity liquid. That's colorless in this image here. You can see the non-uniform displacement from a macroscopic point of view, but also we can see what's going on from a pore scale point of view. You can see the water phase invading the pore space, and you see the trapped oil ganglia here. And the other type of visualization is a three-dimensional visualization of a three-dimensional porous media. And we use confocal microscope to do this visualization. This was following the work of Sujit Datta, who opened this meeting yesterday. So the idea is to get a glass bead packing and then use confocal microscopy to try to visualize the flow in this 3D structure. If you can stack the image from the different slices, and then you can get a renderization of the image. So we improve of the techniques that was presented by Sujit, using two different improvements. The first one is to use fluorescent dye, different fluorescent dye in the different phases. So we can simultaneously see 2, 3, or even more different liquid phases. So in this picture here, for example, water is the blue phase and oil is the yellow phase. And the other also is to use a fast confocal microscope to see the dynamic processes. So in this case, we have an area volume of the media that was fully saturated with oil, which is yellow in this picture. And you can clearly see the water phase invading, and the water phase here is marked in blue. Whatever you don't see is the glass beads. It doesn't have any fluorescent dye on it. Once you get to a steady state, you can get a more higher resolution image. Then we can really get a detailed description of the trapped oil ganglia. And then we can map and study in detail the physics behind that. Again, we published this work recently on these techniques. So the two stories that I'm going to discuss here today, one is the effect of the viscoelasticity on pore scale oil displacement. So it's well known in the literature that if you have a high molecular weight polymer flowing through a constriction and a convergent divergent channel, the polymer molecules will have to stretch to go through that constriction. And then that stretching, the elasticity of the molecule will resist that stretching. And then that shows up in the flow as an extra pressure difference associated with this viscoelastic character of the solution that's flowing. So here's just an example of a pressure drop measurement as a function of flow rate for different high molecular weight polymer solution. If the flow rate is small enough, you get this linear behavior of a Newtonian liquid, but now at high enough flow rate, you get this extra pressure drop associated with the stretching of the molecules. So it's a manifestation of this high extensional viscosity that you see in these high molecular weight polymers. And the question is, can this higher pressure drop in the water phase mobilize trapped oil ganglia? So this problem had been analyzed before by Nielsen et al., but they didn't use a strongly elastic liquid, so you could not really tell the effect of the viscoelasticity. And Clark used similar liquids that we are using here, solution of polymer ethylene oxide, but in a different geometry. So our experiments, we used an oil phase, which was in a mineral phase of viscosity of close to 18 centipoise. We used water phase, and then we used a PO solution with 0.1% concentration. Here's the shear viscosity of this PO solution. Is slightly shear thinning, but in the range of shear rate of the experiment, the viscosity around between 7 and 8 centipoise. And then we use a glycerin and water solution with the same viscosity of the PO solution. So the idea is to compare the flow behavior of this glycerol solution with the PO solution, because if the process is dominated by a viscous effect, they should give you the same behavior. And any difference between the flow behavior of these two solutions is probably going to be associated with this high extensional viscosity that we see in the PO solution. So we do the experiments, and we first saturated the porous media with an oil phase, which is transparent in these images. Then we inject the water phase. Here, the first column is always the water injection. So the water is dyed with the red color. The middle column is the glycerin water solution, and the right column is the PO solution. And we do the experiments, this displacement flow for different flow rates. Here we have in the bottom, the volume of oil that's trapped at the end of this process. So in the first, at low flow rate, you see that the remaining oil saturation of the glycerin PO solution, they're basically the same, and they are lower than the water, and that it's associated with the higher viscosity of this glycerin and PO solution. And as you increase the flow rate, at the highest flow rate, you can clearly see that the remaining oil saturation of the PO solution is lower than the glycerol solution. So at this condition, the Weissenberg number is high enough that the elasticity becomes important. So the elastic force is associated with that extensional viscosity of the polymer solution flowing through this constricted capillary is able to mobilize these oil ganglia. So we can map this oil saturation as a function of capillary number for these different solutions. We can clearly see the water phase gives a higher oil saturation. And then we have the glycerin solution shows the same residual oil saturation of the PO solution at the lower flow rate, but at the highest flow rate explored, we can see that the residual oil saturation of the PO solution is much smaller than that of the glycerol solution. So this difference is associated with the viscoelastic effect, with this higher extensional viscosity associated with the flow of the polymer solution. So here's just an image showing that for the same capillary number and the same flow rate, that the size of the oil ganglia that's trapped in the PO solution is much smaller than the oil ganglia that you see in the glycerin solution. So again, we were able to mobilize this larger oil ganglia, which leads to a lower oil saturation. So the second story that I want to discuss here is the flow of a suspension of soft capsule. And it's a work of many different students. Rafael and Bruno are graduate students in the lab, and Mariana and Deborah were postdocs. So the idea here is that if you have a region that's saturated by oil, if you inject water, water will displace that oil but leave a trapped oil ganglia. But now, if we use a soft elastic microcapsule that's suspended in the water phase to block the preferential water path, it will divert water to different flow path, and then that flow diversion will mobilize oil ganglia. So we need to control the degree of blocking by controlling the size of these capsules so they don't just get filtered out of the porous media. You want them to invade the porous media, and they need to have the right elastic property to be able to block some of the preferential pore path. So we make these tunable elastic microcapsules using a double emulsion template, using a capillary device as was described by Utada et al. And then from the double emulsion, we cross-link the middle phase, which is the polymeric phase. And then by the degree of cross-linking and then by the thickness of the shell, we can control the mechanical properties of the produced capsules. We get these capsules and flow them through constricted capillaries, which would be a model of a single pore throat of our porous media. And you can see here, as the capsule is flowing through a constricted pore, it has to deform to go through that pore, and then the pressure goes up. So there's a maximum pressure that you need to make a certain capsule to flow through. And that maximum pressure is a function of the geometry of the flow. When the important geometric parameter here is the ratio of the capsule size to the pore throat size, and also of the mechanical properties of the capsule itself. So here in the bottom, I'm showing an example of results that we've done with PDMS capsule that we published some years ago, that's showing what's the maximum delta P as a function of the shell thickness and also the degree of cross-linking. So we can make very soft capsules that they can flow through the constriction without a very high pressure difference, but then we can make very stiff capsules that we need a very high pressure difference to make those capsules flow. And then the last step of the research is to try to understand how these capsules can be used in a porous media flow to improve and to displace oil. So the experiment here, we first saturated the porous media with the oil phase, which is dyed in yellow color here again. And then we, in this initial phase, we have some remaining water saturation. So we start the experiment with an oil saturation of around 85% and the remaining water saturation of 16%. Then we inject water at a certain speed and a certain corresponding capillary number. And after the water injection, again, water here is dyed with the blue fluorescent dye. The residual oil, the remaining oil that we get on the porous media was around 33%. So there's 33% of the oil of the porous spaces of oil that's trapped there. So we're injecting water and getting water on the other side. Now we inject a certain amount of suspended capsule and then inject water again. You can see that there's some of the oil that was trapped comes out through the outlet piping. So this was oil that was trapped that we were able to displace. And then if we do an image analysis of the porous space again, we can see that the oil volume trapped reduced from 33% to 26%. So we were able to mobilize some of that oil ganglia that was trapped there. So these microcapsules were able to mobilize the oil that was inside the porous media. So at the end of the process, after we reach steady state, we can analyze in detail the phase distribution within the porous space, as I'm showing here in this video clip. So yellow is the oil ganglia that are trapped. The pink colors are the capsule. So we use a third different fluorescent dye, and blue here is the water phase. So we can get a very detailed description of all the different phases and how they are distributed in the porous media. So we show that microcapsules were able to divert water, and then we can produce more oil using this technique. We need to test this much further. First is to test that in rock samples. So this was a model porous media, and the pore throat size was fairly large if you compare to a reservoir rock. So we need to be able to make these tunable mechanical capsules in a smaller size than what we are making now. We are making now around between 90 and 100 micrometer. That's the smallest size we can make. And we need to get down to around 10 micrometers. And also we need to make these capsules in a large volume so we can use actually in a reservoir. So before closing this presentation, we are also conducting some work on different physics also in porous space. One is a PhD thesis of Paula Hayes. She's studying condensate gas flow. So when the condensate gas is flowing through the porous media and the pressure go below the dew point, you form a liquid phase, and that liquid phase may block the flow path of the gas, so which leads to a drastic reduction of gas production. So this is very a big problem in condensate gas reservoir and in shale gas production also. So Paul is developing a compositional capillary network model in order to describe this phenomena. And also we are doing pore scale visualization. So you can see that the liquid phase and the gas phase are flowing here and we're going to compare the composition of pore network model with this pore scale visualization. And also, Nicole Lima is studying during her PhD foam formation in the porous media. So here we have a porous media that was saturated with a surfactant solution. She's injecting gas. The gas is displacing the surfactant solution. And then we are studying how these dynamics of lamella formation and foam formation is happening. So with that, I want to thank you for your attention. Thank you, the sponsors of the oil porous media flow in our laboratory. And I want to take the chance that when life comes back to normal and you have a chance to travel, I'd like to welcome you to visit if you see our group in Rio de Janeiro. Thank you very much for your attention.